Hello everyone, welcome back to part 2 of this week's session on regression, or part 3 of our regression refresher overall. So picking up where I left off, I'm going to reintroduce the procedure for looking at categorical predictors in regression. So as I noted right at the start of this regression component, a strength of multiple regression is that it's possible to include combinations of continuous and categorical predictors. So let's think a little bit more closely about how to include categorical predictors in regression analyses. So in the case of a categorical predictor that has two levels, a binary or a dichotomous categorical variable, well, actually, we've already seen that in action because participant sex in the analyses we've already been running is a categorical predictor. So a key thing is if we enter that as a covariate in Jamovi terms, the interpretation of that variable depends on its coding. In our case, female was coded as 1 and male was coded as 2. So the coefficient represents the effect of being male rather than female. Okay, so it's the effect of being in this category rather than the other category, and that coefficient would have the same number but the opposite sign, so it would be a minus number if we had coded it the other way around. So if male had been 1 and female had been 2, because it would then indicate the effect of being female rather than male. Okay, so if we'd entered it as a covariate in Jamovi, this would be the coefficient of sex, okay, 0.218. So being male rather than female is associated with a 0.22 higher score in commitment, which is not significantly different from 0. Okay, so when we have binary or dichotomous categorical variables, it's very straightforward. What requires a little bit more thought is when our categorical predictor has 3 or more levels. So let's take that research question that we've been working with about the association between identification, organizational identification, and commitment, and think about another variable that might be relevant. Okay, does working in different departments in the organization predict commitment? So let's say the organization we've been looking at has 3 separate departments. People either work in sales, in development, or in IT. Now, assigning numbers to these, as we might do in our data file, is of course essentially arbitrary. It's meaningless. Okay, those numbers are simply identifiers. They're just labels. So there's nothing inherent in sales that needs a value of 1 or 2 or 3. It's just a label. Okay, so our answer, again, this will hopefully be familiar to you in conceptual terms from last year. Our answer here is to create dummy variables. Now there are 3 categories, okay, in this variable: sales, development, and IT teams or departments. So we would end up with 3 dummy variables. Now, unlike in SPSS, Jamovi allows us to analyze these categorical variables without having to manually create those dummy variables, as we will see. Okay, so using those dummy variables or being able to enter those as a test of the effect of a categorical variable allows us to assess the significance and the explanatory role in terms of R squared of that variable as a whole, of team or department as a whole, while also being able to assess the effect of being in a specific category within that variable relative to a reference category. Now, behind the scenes in Jamovi, when we enter a variable, it will drop one of the dummy variables as a reference category. The reasons for that, hopefully that you'll recall, is that when we have 3 dummy variables for a 3-level categorical variable, our membership of a given category can be perfectly predicted by the combination of the other predictors. So if we know the value on sales and on development, then we will know the person's score on IT. So if they're not in sales or development, they will definitely be in the IT team. Or if they're in the sales team and not the development team, then they're definitely not going to be in the IT team. So what that means in analytic terms is that those 3 dummy variables are redundant. There's redundancy. Okay, so we drop 1 in order to allow the analysis to run, and then that provides a reference or comparison category. Okay, for the rest of the dummy variables, the rest of the categories. Okay, so let's look at that in action. I'm going to go back to Jamovi and our example. So I'm just going to start with a linear regression. Okay, just effectively repeating the first multiple regression that we saw. So I'm adding commitment as our dependent variable. We've got our 4 variables that are covariates. We've got sex as a factor. But now I'm also going to enter team as a factor as well. Okay. Now, in order to assess the overall effect of team, what I'm going to do is build upon what we've just seen in the second part, or the previous part of this session on hierarchical regression. I'm going to enter team in its own block at the end. Okay, so all of these predictors are going into block 1. Okay, and now in a second block, I'm adding team. Okay. Now I'm going to ask for the things that we always ask for: the f-test, adjusted r-squared, confidence intervals, and the beta coefficients. Okay, so this is our output. Again, we have this drop-down option that allows us to toggle between the first model, the first block of variables, and the second model, which then also includes team. Okay, so let's just pop back to the output, zoom in on a few key things. So again, following on from the hierarchical regression analysis, okay, we can now see that compared to the model that doesn't have team, adding team explains an additional 0.003, so less than 1% of the variance in commitment, and that is an amount that is not significantly different from 0. So adding team to the model, or department, does not significantly improve the model in terms of variance explained in the outcome. Okay, again, this value is simply the difference between these two values for the separate models. Now, if we look right down here at the bottom for the coefficients, these indicate the effect of being in a particular category relative to the reference category. It's IT in this case. Okay, so this is telling us the effect of being in the development team rather than IT, okay, and the effect of being in the sales team rather than IT, okay, both of which are non-significant differences. Now, the reference category can actually be changed very easily in Jamovi. So what I'm going to do is just pop back to that output. So let's say, for example, that we were interested in not just the effect of being in the development team rather than IT, or the sales team rather than IT. Let's say we're also interested in, well, what's the effect of being in the development team rather than the sales team? Okay, so if I go back to the analysis and go to this drop-down option set here of reference levels, okay, so we can see here that Jamovi allows us very easily to change the reference category in the analysis. Okay. So for team here, the reference category is IT, but I can very easily change that to sales. And now it has updated the output to tell me the effect of being in IT rather than sales and development rather than sales. Okay, or I can very easily change it so that development is the reference category. Okay. Likewise, I should point out, it's also possible to do that with our dichotomous variable if we have entered it as a factor. Okay, so as I noted, female is the reference category here, so this is this coefficient for sex is the effect of being male rather than female. If I change that round, so female is the reference category, we get the same coefficient, but now it's minus. Okay, it's of opposite sign, as I mentioned earlier. Okay, so that's how you can change the reference category very easily in Jamovi. Okay, so that's categorical predictors, which Jamovi allows us to handle very easily. So to close off this session, I'm going to move on to what is probably slightly newer terrain, newer material for you. And I want to revisit that issue that I posed right at the start with regard to regression, that big note of caution regarding causality. Okay. Now, in all of these analyses, we are testing hypotheses that specify, or trying to specify some sort of, or implying some sort of causal relationship between variables. But of course, as I stressed at the outset, there might be really good reason to hypothesize that one variable affects another variable in causal terms. But if we've only measured those variables rather than directly manipulating our IV, A, then we can't be certain that that relationship is causal, okay, for all sorts of reasons. It could be because of some other unmeasured factor. There could be big confounds of variable A, some other thing we haven't measured that is confounded with variable A. Or there could be some third variable that is actually the cause of both A and B. Or the relationship between A and B might be entirely the reverse. So in this case, the first analysis we looked at, a simple regression, we looked at identification predicting commitment. If, however, we'd also specified, another researcher specified, oh no, it should be the other way around. Identification is what's caused by commitment. Okay, and we run this analysis instead, where commitment is the predictor and identification is the outcome. These two analyses would give us identical estimates, various different types of estimates. So it would give us an identical standardized coefficient. The beta coefficient would be the same as with the t-statistic, the p-value, and the r-squared, okay, the indicator of overlapping variance. So the statistics themselves can't tell us anything about the directionality of the effect or any sort of causal sense of the causal relationship. Okay, all it's doing is assessing, in the end, associations in statistical terms. So one way of trying to get around or trying to get a better handle on potential causal relations is through longitudinal research. Rather than taking an experimental route to testing causality, direct manipulations of certain types of variables, for example, just may not be possible. So one other alternative is longitudinal research. And the basic premise here is that, well, if one of the criteria for establishing causality is that the cause precedes the outcome in time, okay, the cause has to happen before the effect, then perhaps we can just measure a predictor and an outcome at different time points. So we measure our predictor at one time point and then measure our outcome variable a week, a month, or a year later. Okay, so now we're looking at identification and commitment not measured at the same time, but at one time point, and commitment measured a month afterwards. Okay. Now that doesn't actually get us that far. There's still a big problem, because the outcome variable, commitment, could still conceptually be causing the predictor at an even earlier time point. Someone who was suggesting that, a researcher suggesting that it's commitment that causes identification, could simply say, well, maybe just commitment 1 month before this identification measure was taken could be what's explaining identification. Again, identification is being explained by commitment, not the other way round. So a solution, a very rough solution and an imperfect solution to this is what is known as cross-lagged analysis. So the basic methodological feature here is that both the predictor and the outcome variable are measured at 2 or more time points. So however many time points you have, let's just say 2 for simplicity, you're measuring both the predictor and the outcome variable. So you've got 2 at least measures of each. Then what the researcher can do is run 2 multiple regression analyses. So what you do is firstly you regress the outcome at time 2, so let's say commitment measured at time 2, on identification at time 1, the predictor at time 1, but now also controlling for the outcome variable measure at time 1. So you're controlling for commitment at time 1. Okay, so let's just see that. So we're not just specifying identification at time 1, predicting commitment at time 2, we're also controlling for commitment measured at time 1. So this effect here of commitment at time 1, predicting commitment at time 2, is often referred to as the autoregressive effect. Okay, so it's an estimate of a variable predicting itself measured at a different time point. So a time 1 measure predicting a time 2 measure of the same construct is an auto-regressive effect. Okay, so what's the logic behind doing this? Okay, for controlling for the outcome at time 1, the same time that this was measured. Well, it's as follows. So if the outcome at time 1 doesn't explain 100% of the variance in the outcome at time 2, so if commitment at time 1 doesn't explain 100% of the variance in commitment at time 2, then it suggests that commitment scores have changed over time. There is something about the time 2 score that can't be explained by the time 1 score. Okay. Therefore, any variance not explained by the time 1 variable, any leftover variance in time 2 scores, is a change score. Okay, that leftover variance is the extent to which scores have changed between times 1 and 2 in commitment. Now, if another variable measured at time 1, let's say identification, significantly predicts the outcome at time 2 while adjusting for this measure at time 1, it's therefore predicting change in the outcome that must have occurred between times 1 and 2. In other words, after those time 1 variables were measured. So if we say significant association between identification and commitment at time 2, while controlling for commitment at time 1, what it suggests is that identification at time 1 predicts change over time between times 1 and 2 in commitment. Okay, let's take that a step further. You can go and also then predict or run a regression analysis for the predictor variable for this, and this is a way of testing the reverse causal relationship. Okay, so let's say in our previous example here, identification predicts change over time in commitment. Could the reverse also be true? Could commitments be predicting change over time in identification? Well, we can also test that. That's part of the fully cross-lagged model. So we run a regression analysis in which identification at time 2 is the outcome, and commitment and identification at time 1 are the predictors. Okay, so here we've got the auto-regressive effect, identification at time 1, predicting identification at time 2. Now, if commitment at time 1 does not predict change over time in identification, then it seems to suggest that the predictor, identification, predicts change in commitment over time, as we saw on the previous slide, but commitment at time 1 does not predict change over time in identification. Okay, so identification predicts change in commitment, but commitment does not predict change in identification. Okay, let's see that in action, because although that sounds a little bit complex in terms of the logic, actually all it requires is 2 multiple regression analyses which actually have the same predictors in them, as we'll see. So let's go to a second data set here, in which we have each participant's measure of commitment at time 1 and commitment at time 2, identification at time 1 and identification at time 2. Now, just to point out, this is because each participant's scores are all in one row. These data are in so-called wide format. So this is actually a form of repeated measures data. So we've got each participant's 2 commitment scores and each participant's 2 identification scores. They're providing 2 scores for each construct, one at time 1 and one at time 2. Okay, now these are in wide format as opposed to the long data format that we were using for the mixed models. So for this longitudinal sort of survey type research or data that comes from that, for the analyses we'll be doing, we need the data in wide format. Okay, so let's see what we do in analysis terms. We go to regression, linear regression, and we want to run an analysis in which we have our 2 time 1 variables, commitment and identification, as predictors. Now let's first of all look at commitment at time 2 as our outcome variable. Okay, let's move that across. We want to ask for the usual things we ask for, our f-test, adjusted R squared, confidence intervals, and beta coefficients. Okay, so let's just have a little look through the output here. Okay, so what we have is, of course, commitment at time 2 and commitment at time 1 as a predictor of that. This is the auto-regressive effect. Okay, the coefficient 0.59, the beta coefficient 0.61. Now we can already see from the R squared values here that commitment at time 1 and identification at time 1 explain much less than 100% of the variance in commitment at time 2. Okay, only around about 44-45% of the variance. So there's a lot of variance left over to explain. There's a lot of change that's happened in commitment scores between times 1 and 2. So now we're looking at whether identification might be explaining some of that change over time. Okay, that's the coefficient, t-statistic, and the p-value, and the beta coefficient. Okay, and that's significantly different from 0. So it does suggest that identification at time 1 is predicting change over time in commitment scores. Okay. Now, let's look at the reverse causal relationship. Okay, so we've seen that identification seems to be significantly predicting change over time in commitments, but does commitment predict change over time in identification? So what I'm going to do is just very simply duplicate this analysis. It's a little bit quicker. I'm just right-clicking, going to Analysis and Duplicate. Okay. And all I'm going to do now is swap out commitment at time 2 as the DV and put in identification at time 2 as the DV. Okay. So the predictors, commitment and identification at time 1, stay the same. Okay. Now, just having a quick look at the R squared values. So yeah, only around about 35-36% of the variance in identification at time 2 is explained by this model. So quite a bit of change has occurred over time as well in identification. This is the auto-regressive effect. So identification's slope on itself is 0.56 unstandardized and standardized 0.58. Now the key thing here is whether commitment at time 1 is predicting this change over time in identification. Okay, let's look across here. That's the coefficient, standardized coefficient, t-statistic, and the p-value. That's non-significant. So what this suggests is that commitment at time 1 does not predict change over time in identification, but as we saw in the previous analysis, identification at time 1 predicts change over time in commitment. All right. So we can then extract or just to read off the coefficients for these effects, and we can draw out our cross-lagged analysis. This is the fully cross-lagged model by adding the path values and their significance as a way of basically reporting or summarizing the analysis in this path diagram format. Okay, so in this case, these are the beta coefficients. So here we have identification predicting itself over time, commitment predicting itself over time, and these diagonal arrows are whether they are predicting the opposite variables change over time. So we can see here identification predicts change over time in commitment, but commitment does not predict change over time in identification. All right. So this is an approach which, if we have good and reliable longitudinal data and this fully cross-lagged panel design, as it might be referred to, this can do or go some way to increasing our confidence about the nature of causal relations amongst the variables, because it allows us to look at whether one thing is predicting change over time in another. Okay, but not entirely. Okay, unless variables again are manipulated, there's always a degree of uncertainty about causal relations, because, for example, each of these measures might be confounded with something else. All right. One final thing to note here is that, technically speaking, okay, the effect here of, say, identification on change in commitment, what we're saying here is that between person variation in identification, so someone scoring higher in identification at time 1 changes more, or their change over time is bigger than it was for someone who was lower. Okay, so it's between person variation in identification predicting change over time in commitment. Okay, so it's not change in identification predicting change in commitment. All right, so that's just a little technical note. Okay, so that's it for this third and final regression session, although we will be picking up the regression theme next time round when we introduce mediation and testing indirect effects. Okay, thanks very much in the meantime, and yeah, see you then.